So in this lecture, I'm going to talk a little bit about programming languages, their uses and differences, and why we're choosing one over another for this course. So yeah, another cute, short little lecture. Again, this is a section in the book, Introduction to Real-Time Computing for Mechanical Engineers. Check out the website, rtcbook.org, for more info. Buy a copy, why not? Good. Introduction to Programming Languages. So this is our perspective in this course. Processors understand low-level machine language, numerical instructions, and data, such as the binary shown in the figure. So instructions and data ultimately get saved in memory like this, as numbers, ultimately binary numbers, and each address in memory has contents that are encoded with a number. So here I think we have 32 bits representing either a piece of data or an instruction for the processor. A program is a sequence of instructions stored in memory, with each instruction specifying an operation to perform, so it can be represented as a sequence of numbers. So this we could be looking at right here, a program, a sequence of instructions. High-level languages like Python or MATLAB simplify programming by abstracting hardware-specific details. So each processor has a set of instructions, and that processor is going to require that those instructions are used, and they're used in a certain way. Now, we don't want a program that we write to be specific to one processor made by one company. So we have these higher level abstract languages that can be interpreted into or translated into the machine language at the lower level, and can be written in general for any processor that has a set of tools called compilers. That's the main tool that take the or interpreters that take the high-level description of the program and translate it into the low-level machine code for that specific piece of hardware. Okay, assembly language provides a human-readable layer above machine language with a one-to-one mapping of instructions. So an instruction in machine code is a number. If we give that number a symbolic representation, say load or plus, something like that, a very low-level operation, we can give it a name, and that would be assembly language. It's human readable. We'll see some examples of it, but it's challenging to write complicated code in, so that's why we prefer to use a programming language. And the hardware-specific abstraction is also useful. Another reason to use a programming language instead of assembly language, which is specific to each processor. Modern programming uses higher-level languages like C, which offer processor independence and enhanced readability. Looking through assembly code, it's often very difficult to discern what the program is doing. Whereas when you look at a C program, if the programmer was doing their job well, you should be able to follow what's going on. Okay, so that's high-level intro to programming languages. The translation aspect of programming languages. So high-level languages are translated to machine code through one of these two processes, either compilation, which converts the entire program into optimized machine code before execution. So this way of doing it has faster runtime than the other way. Runtime is the time it takes to execute the program. Interpretation, which executes source code directly, translating it on the fly, which is more flexible but slower. Interpreters, you can give it a line of code, it will interpret it and spit back the result. Compiled code, you have to have the whole program at once before you can compile it. It allows you to do some runtime efficiency improvements. The program that does this is called a compiler. And compilers are often highly optimized. So that's why highly optimal and optimized code is often compiled, whereas code that's not as highly optimized can be interpreted. It's much more convenient to use interpreted coding techniques, but compilation often is the way to go for real-time computing, embedded computing. C is primarily a compiled language, balancing performance and abstraction for real-time computing. It's typically compiled. There are very few attempts to use C in an interpreted environment. We used to talk about programming languages as either being compiled languages or interpreted languages. That terminology is kind of on its way out because people are writing interpreters for typically compiled languages and compilers for typically interpreted languages. So that's gotten a little bit fuzzy. So now we say typically compiled or typically interpreted, and C is typically compiled. The figure outlines the translation process. So we have our C program source code here. The extension that we usually use is .c for code files, and then .h for header files, which are also code files but have some information that we usually want to keep out of our .c files. We'll talk more about that later in the chapter. So here are our source files that we write our programming language programmed files. We write our programs in them. And then we give that code to a compiler. Okay, the compiler in C, there are different compilers. We're going to use a specific cross compiler that's made for the type of chip. We're going to use a compiler that's made for the type of processor on the MyRio, which is an ARM processor. We'll talk a little bit about that later on. But that compiled code that comes out is in assembly language, and it's usually given the extension .s. It's then given to an assembler, which produces a machine language object module. So now we've gotten to object modules in machine language. So now we're talking about binary code that has instructions and data in it. And we have a linker, which brings in some other objects from libraries. So sometimes those library objects that we bring in are functions, for instance, or maybe constants as well. And these are made by libraries that are used in our code that are not part of the base language, C language. What comes out of the linker then, so that goes to the linker. The linker links up library objects to our machine language object module, and what comes out are machine language executables. So in a Linux environment, which we're using on our target computer, it's a .out file. In a Windows environment, it would be a more familiar extension, the .exe extension. We give this executable to a loader, which loads the program into memory. So then it's ready to execute. Okay, so this is the process going from a source code file to a program that's ready to run in memory. All right, so we have this process that is handled for us in the IDE. It's handled for us by Eclipse. We have set up a compiler, assembler, linker, and loader so that we can do all of this within one program, the Eclipse IDE. We can write our source code and all the way to running it in our IDE, which makes it very convenient. Otherwise, you have to run separate programs for each of these, which is inconvenient. Okay. Good. So finally, why use C for real-time computing? I said we're going to use C at the very high level of abstraction here. We have LabVIEW, which you can also program the myRIO boards in. Simulink is something that MATLAB includes. That's a very high-level graphical programming language. A little lower level would be scripting languages like Bash, Perl, BASIC. And then you get into the typically interpreted languages that are usually pretty high level: MATLAB, Python, Ruby. Then you get into the typically compiled languages: C++, Java, some examples, popular examples. And then C is, we're putting that right above assembly language and below the typically compiled, although it is a typically compiled language, it would include C as well, but it's a little bit lower level than C++ and Java. These have some higher levels of abstraction going on than C does. So C is where we want to be. And why is that? First of all, efficiency. It has a small size in memory, minimal runtime overhead, and optimized compilers make C fast and power efficient, which is often good for real-time and for embedded computing. Memory manipulation. It provides low-level control over memory for real-time tasks. Sometimes we want to get to that really low-level memory manipulation for real-time computing tasks. Ubiquity. C compilers are widely available across processor types. It's one of the most available type of compiler. So if a processor has any language compiler available, C is usually the one, and then the more abstract you get, the more rare the compilers are, but C is a very common one. And also for balance. So C strikes a balance between abstraction and control, sitting close to machine code without being processor specific. So it's a balance between the nice abstraction that you get at the high level, get that nice abstraction, and the control that you get at the low level. Yeah, so that's why C. It's the most popular by far. I think last number I saw was it like 80 or 90% of real-time and embedded computing projects are done in C. So that's the one that we'll use. Yeah, and I think you'll learn to love it. Oh, don't worry if you don't know it yet. I don't assume anybody knows it at this point. We're going to learn it together as we proceed in the best way, which is by applying the language to a specific project to do some task that's pretty cool. And it involves hardware. So what more could you ask for? All right. I'll see you next time.